Okay. So today let's say a little bit more about how do you construct a finite difference operator, right? So we have actually studied only a small number of finite difference operators. The first derivative in x, we studied 3, forward, backward, and central difference. We studied the second order derivative in x and in y. They are basically the same. And all of them applies to Cartesian structured grid. And even in your project, unless you are doing it the other way, in the non-suggested way, you are still going to be using simple finite difference operators on Cartesian grid. Right, so there are some people who came up and say, okay, I directly discretize the finite difference operators on the skewed curvy mesh, which is great if you can do that, but it's actually more work than if you convert the differential equation and then discretize it in the Cartesian domain. So today let's talk a little bit about if you don't have the luxury of converting anything into Cartesian domain, or if you have to discretize some differential operators you have never seen before, what to do. Okay? So the way to construct a finite difference operators is actually no difference from the way we verify that a finite difference operator actually works in the first place. So let's just give a simple example of how that works. So for example, if you want to construct a finite difference operator over, let's just imagine a very weird mesh. Let's imagine if you want to discretize some finite difference operators on a honeycomb. All right. So this is never kind of tried this example before, but I think it's fun to do this. So let's say this is your mesh. You have a point here, x and y, okay, and let's say this is your delta. I'll just write as delta, not delta x and y, and basically you have 60 degrees angle. Basically, you have 120 degrees angle between them. Basically, it's a perfect isotropic mesh, but not in the regular way. So how do you do finite difference on that? Right, so the technique you're going to learn actually applies to different finite difference operators and different mesh. So let's just figure out you want to compute the derivative of w on x at this point. Okay, so the stencil you want to use is my w at center. All right, my w up, w left, w right. Okay, let's just say WC, WU, WL, and WR. So this is the center, this is up, this is left, and this is right. All right, so simple stencil. And how do we do that? How do we derive what finite difference operator we can use to get dw dx? Any suggestions? Yeah, Taylor series, right? So basically the idea is we do Taylor series and determine the unknowns. So Taylor series, and 2 is just to combine different terms with unknown coefficients. And 3, solve for these unknown coefficients by trying to cancel as many terms as you can, trying to get the highest order scheme you can. All right. So for this case, let's just see how the Taylor series would play out. So WC is just equal to WC, right? So because we expand at the center, that's probably the most convenient. W up is equal to WC plus the derivative in y, right? And times delta plus, let's just aim for a, so let's actually figure out how many terms we can cancel here. All right, so how many terms we can cancel here? We have 4 different coefficients. We first want to cancel the WC, right? And then we want to cancel dw dy, because what we want is dw dx. So that's giving us 2 equations. And 3, we want to actually get our dw dx. So that's 3 equations. And we have 1 more degree of freedom to play with, right? So what do we do with that? Can we use that to get actually a second order term? A second order, can we use that to get a second order scheme? Yes? Oh, unfortunately, no. Because in 2D, there are many second order terms, right? There is a term proportional to delta x squared. There is a term proportional to delta y squared. There is actually another term proportional to delta x times delta y. There is no way we can actually get a second order term. So in this case, one of the very conventional thing to do is actually just to give up trying to get a second order scheme. As opposed to doing that, try to make the scheme as stable as possible in the general sense by actually minimizing the coefficients themselves, minimizing the magnitude of the coefficients themselves, sometimes often in the least squares manner. So let's see what we get. Okay, so this is plus O delta square, right? So we'll just not expand any further, because we know we won't be able to cancel all the delta square terms. So W left is WC. Now, what is it? W left is actually positioned at minus square root of 3 over 2 delta and minus half delta, right? So this is in x and y. So we have 2 terms. One is actually proportional to partial x, and that is multiplied by minus square root of 3 over 2 times delta. And there is another term in partial y times minus delta over 2, right? And then we have this O squared term. And W right is very similar, but instead of x positioned at the negative side, x is now positioned on the plus side. Make sense? Okay, now the 3 equations we want to enforce is, if I combine them with a unknown coefficients, let's say a plus b plus c plus d, what we get is, this is this a, b, b, and c, 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 and d, d, and d. All right. So the first equation is just this equation gives us a plus b plus c plus d equal to what? 0, right? And the second equation is with x, right? So basically we want them to be approximate to dw dx. So the second is that these 2 terms is going to give me c plus d has to be equal to not c plus d. C plus d has to be weighed by different things, right? So minus square root of 3 delta times c plus the same thing has to be equal to 1. So that's what's supposed to be giving me the derivative. And now this is going to give me both are minus delta over 2, c plus d is equal to 0, right? The second, oh yeah, I also have this, right, thanks. Then plus 2b actually. Let me wait, what happens? Okay, so yeah, let's rewrite it. So we have delta times b minus the average of c plus d has to be equal to 0. And that's it. That's the 3 equations I have.